this environment. I'm using Abaqus 6.13 and you are using Abaqus 6.14. It does not matter. First, and go to the parts, double click these parts. I just name it round bar, and then 3D deformable solid extrusion. Approximate size use 150, and because the length of this bar is 100 millimeter, it does not matter. You can just use 150, and you should also know that because Abaqus does not have its own units, you need to specify the units based on the sheet I just gave you last time, right? So press continue, and then we will be led to this environment, and we are going to draw a circle for this is a cross-sectional area, and we use this this tool, click circle, center, and perimeter, and click it, and I'm going to use this origin as the center. I'm using the highest point as one point on the perimeter. So I will have this circle. So you can draw other circles also, but I only need to use one circle. So that's the reason I'm going to cancel this procedure. Now, after I draw this circle, I need to dimension it. Okay, so I use this tool and dimension, and then click highlight this circle I just created, and then here this is radius is shown here, but what I give you is 15 millimeter diameter, so you need to enter 7.5 millimeter, and then you just press the button enter. Right now you have this circle with a diameter with a radius of 7.5 millimeter. Now I just say I have finished, cancel procedure. Now I can press done here, and then this dialog appears, and how long you want to extrude, and this is cross-sectional area. So the length is 100. I just enter 100 here. Press OK. Don't touch any of these two options. So then I have a bar here. So this is my first step. I have created a bar of 15 millimeter in diameter and 100 millimeter in length. And second step is material. I create a material. So this material is the AISI 1005. And then I go here, mechanical, right? Click this mechanical for the elasticity, and click this elastic. Then this dialog appears. So I need to enter the Young's modulus, which equals 210 gigapascal, and mu equals 0.3 gigapascal. As I told you guys, length we use millimeter, and force we use Newton. So we are going to the Young's modulus, the stress, Young's modulus should be written in the unit of megapascal. Okay, so as a result, this is Young's modulus, which equals 210 gigapascal, and should be written in this term 210. This is giga. Another 3 zeros, 1, 2, 3. That means I have 210 K megapascal, which equals 210 gigapascal. The Poisson ratio equals 0.3, and then we just take care of the elasticity. So we just click OK. Now I have created the material. Look at this one. This is the number 1 appears within this parameter. And then next step is I create a section. And this section I just say round bar. You can see round bar. So solid, type homogeneous, then click OK. Okay? So you need to know that the section is associated with material because we have only created one material, so there is only one option. an ASI 1005. You can just select it and then press OK. Now, we have created one section. So next thing you need to do is just go back to the parts and click, this is a red bar, and go to the section assignment and double click it. After double click it, and so this is statement appears. Select the region to be assigned a section. So I'm going to assign this section to this whole bar. So I click the whole bar, but I can click this off. Right? Then I press done. And then this dialog appears. So which section you want to associate this bar with? I want to say round bar, section round bar. This is the bar, is a section I just created, and press OK. So you can see my bar becomes a green one. So next step, go to step, okay, and click this one. You will see the initial step is created by the system by default, and you cannot change it. And what you need to do is you just create another step, and we just call it step 1 for the procedure type, and just use the static general and continue. So the description, you can write what kind of description you like. Time period, we use 1, and this is the nonlinear geometry, nonlinearity, and you can just click on. This is just for safety reason, and press this OK. And then after you create this step, and then you can assembly here. Come to the assembly, okay, and instance. Click this instance. So the parts. So you use the independent mesh, and it does not matter. You can come back and to change to toggle. This is the dependent on later. But yeah, I would like to use the independent mesh. Then press OK. Assembly I created after I create this instance, and this bar becomes green, right? And then I apply boundary conditions. Go here, boundary conditions. So what kind of boundary conditions I want to apply? Look at the picture I give you. The left hand is fixed on the wall. I just boundary 1, and you use displacement and rotation, and then continue, and then I select this left end, and then done, and then I need to constrain all these 6 degrees of freedom, and U1, U2, U3, and UR1, UR2, and UR3, and then click OK. This is my first the boundary. Are there any other boundaries? We only have one boundary, right? So, and after you finish ending these boundaries, and I would like to you guys to double click these BCs, click this manager, okay, and you need to make sure and this step is started from the initial step, and press left. Now I'm okay now, and then I can, and this is 3 ends. So loads here. So double click these loads, and which step I want to end these loads to? Step 1. I want to end concentrated force. Okay, because I have 2 concentrated force. One is F and one is P. So I'm going to continue. Press this continue, and then you need to be very, very careful about the directions of these forces. So look at this one. So this axial axis is the Z, but in our handout, the axial axis is X. You need to be very, very careful. So the axis in which F is applied is similar to the x-axis in this is Abaqus. So you need to rotate this bar because the left end is fixed. I want to end these 3 loads on the right end bar. So I need to use this tool to rotate the wheel, right? And go here. Then I select the points for the load, and because these two loads F and P, they are ended at the center of this right hand end bar, the red end. So I need to select this is the center. How can I select the center? Go to these tools here. I can define the reference point. These points are highlighted. This means that you can select one of them, define them as the reference point. So I can select, just have one, select this center, okay? Just press once. So here see RP1. So reference point is selected. And then after I select it, I just click this X to cancel this procedure. Now, select point for the load. Okay, after I do this, the RP there, I can select this RP1, okay? Then I press done. Then this dialog appears. As I told you guys, and you need to be very, very careful about these directions of these forces. On our handout, the P is the axial axis is the P is in axial axis. The axial axis in the MATLAB in Abaqus is in the negative z direction. So the z direction means the 3, okay? So that means this needs to be negative because it is going to be acting in the negative z direction. So this is a P's value equals P's value equals 400K. And this 400K, 4.0 kilonewton. This is 4,000, and you need to use Newton, right? And look at the force. Another force is in the negative x direction in the Abaqus. So you say F1 negative 550 Newton, and then I click OK. Now you can see that I have applied two concentrated force. One is axial, another one is perpendicular to this x-axis. Next step, I have finished ending these two concentrated force. Then I need to apply a torque. How to apply a torque? Okay, how to apply torque first? And you need to establish a constraint. Go here, okay? I establish this constraint, and the constraint 1, you can just name it constraint 1, and then press the coupling, and then continue, and then this is a statement. Select the constraint control point. I want to select the reference point I just defined, okay? Okay, I defined. Done. Now select the constraint region type. Region, you want to couple this reference point to what? I want to couple the reference point and to the surface. Which surface? And this the right hand surface. And then I click done. Now this is coupling, so you need to make sure that this is kinematic coupling and don't change any of these settings. So let's click OK. Now look at this. See, if you enlarge it, and you can see here this one leg, and these 3 legs extend from the reference point and to this surface. And then after I do this, I can apply the torque. I can apply torque. I go to the loads again. Okay, double click these loads. Now this time I'm going to apply a torque. The torque is a moment, right? So I can go to click a moment here, and then continue. Make sure this from the step 1 as well. Go to the step, and select points for the load. Select this reference point, and then I'm done. Okay, so as I said, so this is the z-axis. Z-axis is the axial axis. So the torque is about this z-axis, and about z-axis, it is this way. It's a negative z, right? Negative z in negative z direction. So CM3 negative. What is the torque is 20 and 25 Newton meter. We just 25. 25. You should know that the millimeter length we are using millimeter. So 25 newmeter should be converted to 25,000. This will be Newton times meter, right? 25,000, and press OK. Now we have finish adding all these three the loads, the 2 concentrated forces and 1 and the torque. So before we move on to next step, we need to right-click these loads and go to the manager. And okay, so these two guys, load 1 contains these 2 concentrated forces, and load 2 contains the torque. They start from this step 1. We are okay now, right? Now we have finished all these important points. What is the next point? Next point is measure the part by using tetrahedral elements. Okay, how to do it? And go to the module and click this one, and you go to the mesh. Okay, go to mesh. You can see this golden bar. Okay, golden bar. There are several sub-steps. And first sub-step is seed part distance. So seed part distance, the approximate the global size. And you can select this one. This one and 2.1 is by default is the default value, and this one can be used as your causes mesh. But later on, you need to refine this mesh by reducing this number and to get a series of the meshes for this one, and then do the convergence test. From now, we just use this 2.1 and then click OK. Right? Then done. Press done. You can see clearly. So this one, this size, and this size, they are seeded. Then OK. Done. So next one is use this button, assign mesh element. And as I told you guys, you are asked to use tetrahedral elements. Select tetrahedral and technique free and OK. I'm done, right? And then press this button, assign element type. So use the standard and use the 3D stress because we are 3D. Okay, geometrical order, and we use quadratic. You can use linear, but I would suggest you use quadratic because quadratic and its convergence faster. So tet means tetrahedral, and don't change any these options here, and then press OK. Now, then the very last step for this meshing is that use this. Click this one, mesh part distance. And OK to measure the part distance, you can press yes, because we only have 1. Now you can see this meshed this bar. Now up to now we have finished all these steps. Next step will be that we'll create a job and submit it. Double click these jobs here. I can just say run a bar. Continue. Use this model I just created, and click continue, and don't do anything there, and press OK. Okay. Now then you can see, and you have created a bar. Now right click it, so this dialog appears, and so these options appears. You can select submit. So you can see, so this one coloratical elements, this give you the basic information about the model you just created, and here this says running. And when this guy is running, and you can right click again and click monitor here, and go here, and you will see the progress of running. Okay, there are some error messages here. Let me figure out what the problem is.